In this video, I'm going to present the solution for the final challenge problem, the fourth challenge problem, in which you are asked to prove that f of a equals log base e of a. The first thing that needs to be done, absolutely needs to be done, is that we need to prove that f of a to the n equals n times f of a for all n in R. That is, for all real numbers n. Okay, so we will prove this in the following steps. We will prove it in first when n is a positive integer, and then we will prove it for the case when n is a negative integer, and then we will prove it for when n is a rational number, and that will be done in two steps. One in which n equals 1 over m, where m is an integer, and the next step for when n equals p over m, such that p and m are integers. And then we will make the case that the statement is true when n is an irrational number. And from there, we should be able to complete the solution. Okay, so first case, when n is a positive integer. Okay, so we need to prove that f of a to the n is equal to n times f of a. So our first case, f of a squared equals f of a plus f of a, which of course is equal to 2 f of a. So it's true in that case. In the next case, f of a to the third power is equal to f of a squared times a, which of course is equal to 2 times f of a plus f of a, which of course is equal to 3 f of a. And in the next case, f of a to the fourth power is equal to f of a to the third power times a, which of course is equal to f of a to the third power plus f of a, which is equal to 3 f of a plus f of a, which is equal to 4 f of a. And it goes on forever and ever and ever. So for any n, f of a to the n equals f of a to the n minus 1 times a, which equals n minus 1 times f of a plus f of a, which of course equals n times f of a. So that is the case for positive integers. Now, when n is a negative integer, this statement is still true. So let n equal negative k for some positive integer k. Then f of a to the n equals f of 1 over a to the k. Since f of 1 over a to the k equals negative f of a to the k, we therefore have f of a to the n equals negative k times f of a, and negative k times f of a is the same as n times f of a, since n equals negative k. Okay, and so f of a to the n, once again, equals n times f of a, and we've proven the case for when n is a negative integer. Now, for when n is a rational number, so let n equal 1 over m, such that m is an integer, and then we have f of a to the power of 1 over m equals 1 over m f of a. That is what we need to prove. And to prove that, we will let a sub 1 equal a to the power of 1 over m. If that's the case, then f of a sub 1 to the m power equals m times f of a sub 1. And if this is true, then f of a equals m times f of a to the 1 over m power. If we divide m on both sides, we get f of a to the 1 over m power equals 1 over m times f of a. So we have now proven it for rational numbers. or no, wait, no, we still have to prove this. Sorry, we're almost done proving it for rational numbers, but now we have to prove that it is the case for when n equals p over m, such that p and m are integers. Okay, so we need to prove that f of a to the p over m equals p over m times f of a. Note that f of a to the power of p over m equals f times a to the power of 1 over m, and that to the power of p. Okay, that equals p times f of a to the power of 1 over m, and that of course equals p times 1 over m times f of a, which equals p over m times f of a. Okay, now it has been proven for rational numbers. Now we need to prove that this is true for when n is an irrational number, and this is how we do that. Okay, so we're going to prove that f of a to the n equals n times f of a for an irrational number n. We're going to construct two sequences of rational numbers, alpha 1, alpha 2, on and on and on to alpha m, and beta 1 and beta 2, on and on and on, until we get to beta sub m, and it keeps going. All right? And so we're going to construct these two sequences of rational numbers, alpha sub m and beta sub m, such that alpha sub m is less than n, and beta sub m is greater than n, and the limit of alpha sub m as m goes to infinity equals the limit of beta sub m as m goes to infinity, and they both equal n. Those limits both equal n. Okay? So, all right. So, since f is increasing, we know that f of a to the power of alpha sub m is less than f of a to the power of n, which is less than f of a to the power of beta sub m. Okay. Or, since alpha sub m and beta sub m are rationals, alpha sub m times f of a is less than f of a to the n, which is less than beta sub m times f to the a. Okay, so those two expressions are true. And if we divide all sides by f of a, we get this expression. Alpha sub m is less than f of a to the n over f of a, which is less than beta sub m for all m. And therefore, the limit as m goes to infinity of alpha sub m is less than and or equal to, or less than or equal to, f of a to the n over f of a, which is less than or equal to the limit of beta sub m as m goes to infinity. Okay. And if that's true, then that must be true, that the limit of m, the limit of alpha sub m as m goes to infinity is equal to the limit of beta sub m as m goes to infinity, and are both equal to n. Okay. Therefore, f of alpha to the n power over f of a equals n. And this means that f of a to the n power equals n times f of a. Okay. Okay? So, now that we have proven that that is true for irrational numbers, we can now prove that f of a equals log base e of a. Okay? F of a equals f of e to the power of log base e of a, which equals log base e of a times f of e. And since f of e equals 1, then that equals log base e of a times 1, which equals log base e of a. Okay? And so f of a equals log base e of a, and this completes the solution.